Marcelo Gonzalez, you're a quantum engineer from Qnami, and I think Qnami are building quantum sensors for NV magnetometry, right?
Exactly.
Awesome. So, I mean, I'll let you take it away.
Yeah, I'm just going to share my screen for the presentation. Oh, thanks for the quick intro. I'm just going to make this presentation mode. So yeah, I mean, we are a quantum sensing company. Just probably a little bit about myself. I did material science and engineering masters at EPFL. And during my master thesis, I was able to work at Unibas here in Basel, Switzerland, with the university and with Qnami. And after successfully defending my thesis, I was able to join the company as a quantum engineer, working a little bit on the same project I was doing during my master thesis, but then really focusing on what we're doing here as a company for the quantum sensors. Probably a little bit about us. We were founded in 2017, so not so long ago. Right now, we are currently 12 people. 9 of them have PhDs with a compound of 44 years experience in quantum. We very recently finished our Series A round of funding for 4 million francs, which is good. We're really looking forward to expanding and hiring people. I will talk a bit about that at the end of the presentation. Last year, we had a sales revenue of around 1 million francs, which was quite good for us, and 300% compound annual growth rate. We do have several international partnerships. I'll probably mention a lot more about Horiba, which is one of them, but we work with several universities and research centers with both our quantum sensors and our microscope. So probably just a little bit of an introduction. There are a bunch of quantum sensors that can be found around various different applications. Here I mentioned several of them. First, in the semiconductor industry, I talk about this one first because it's the one we are really focusing on right now, where people are really trying to go for smaller and faster chips or better chips. I will talk about that a little bit later. You could also find quantum sensors in healthcare because people are really looking for higher sensitivity instruments or maybe smaller instruments at work. You can also find them in transportation for autonomous driving, or in energy for renewable energies, or probably measuring the currents of batteries or applications like that. And also in defense, it might be very similar to transportation. But I really want to focus on the semiconductor industry. Because we really do think that there is going to be something which we call computing beyond Moore's law. And in this beyond Moore's law, we really want to focus on the central role of magnetism, or what magnetic properties of materials can do in computing. I will try to really focus on two main different things. One is what it's called MRAM, or magnetic random access memory, where people use magnetic tunnel junctions as their bits. Or in quantum computing, where really people, as you could have seen from the last talk, people are really focusing on quantum computing. There are various different types of qubits. In the case we want to focus on are on probably superconducting qubits, or this magnetic flux qubits. But I really wanted to focus on this because this, for us as a company, really showed that there's a massive investment in this next generation of computing, at least first in quantum computing. As you can see here on the left, there's a bunch of investment put into companies, both from the government or from investors, to really focus on this next generation of computing. But I also wanted to show, this is something that for us was very, very interesting here in this graph on the right, where you have this spin transfer torque magnetic random access memory. This is really probably the next type of memory that people are trying to use. And as you can see here on the graph, throughout the years, they're really trying to, let's say, couple or put together, let's say, bits into smaller and smaller let's say sizes to go into Internet of Things, or this 28 nanometer modes for flash or cache. But as you can really see, oh, sorry about that. As you can really see, there's really a metrology technology limit. And here is where we are really trying to focus on, or we as a company think that we can do a change into the metrology of these types of technology. Because in their existing metrology solutions, they really have a limit both into magnetic measurements. They really cannot do many magnetic measurements, at least not quickly or in what they're looking for. They cannot detect details really at the nanoscale, so below 100 nanometers, most of their disinfectant inspection fails. And also some of these metrology tools do not work in cryogenic environments. And from these problems, this is really where we come in, because we produce quantum sensors, which are based in nitrogen vacancy sensors in diamond, as you can see here. And well, there are many interesting physics inside these type of quantum sensors, which I'm not going to talk about right now. But if you have a question about them, please ask. And really think that this quantum sensor can work as a metrology tool to overcome all of these problems I had been mentioning before. It does have a very high sensitivity per unit volume. It is really self-calibrated. They can last for a very long time, and most importantly, they can work both in room temperature as in cryogenic temperatures and in vacuum. But of course, you're saying, okay, well, these quantum sensors seem very interesting. Why are people not using them by now? Well, of course, there are several different challenges here. I really like this image because it crudely portrays how probably big diamond things are, let's say, manufactured or fabricated, or let's say in this case, cut. But one of the first main challenges is the nanofabrication of diamond. Here at Qnami, we really focus on these nanofabrication, and we have several expertise which are related to the nanofabrication of diamond, and really think that we can produce these quantum sensors in the shapes that we want, or in the sizes or in the chips that we want, to be able to use them as a metrology tools. And then, of course, whenever you're talking about quantum, you have you're talking about quantum sensing, you're talking about photons, you're talking about coupling to optical fibers, you're talking about various different things that require a bunch of technical expertise that we have here at our company to be able to couple all of these things together. So really here, let's say in a nutshell, what we do at Qnami is we design solutions for people that don't really have this quantum expertise. So it's really helping people use quantum sensors to solve the problems they're having without really needing to know how this nitrogen vacancy works. So as I had mentioned a little bit before, we do microengineering and this synthetic diamond. So we really have these like fabrication of our quantum sensors in diamond, and we have to integrate them into a system. In this case, we use them in atomic force microscope, or for magnetometry, to be able to sense magnetic fields. Besides being able to first fabricate the diamonds and put them in a microscope, we also need to have quantum control and data acquisition. So we do have our own software, which is open source and which is also Python based. And then besides that, we of course need to also have these data interpretations. So for all of this, we really require, let's say, various different people, probably like you, or some of you have experience on either microfabrication in diamond or on various other different materials, or using an atomic force microscope, or really creating mechanical parts to be able to use into a system. Maybe you have worked a lot in software, and you know a little bit about how it works with gathering the data from sensors and implementing a software, or really creating a very nice looking interface for our software. So we really require all of these things and all of these various different people at our company. So here, just as a comparison, as what we are proposing as a product, and what you would get or what you would need to be able to solve these metrology problems. Here's a comparison in between our quantum microscope and a synchrotron. There's really no comparison. So the amount of money that you would need, or the amount of people that you would need to be able to get the same amount of information from a synchrotron or from a tabletop design microscope as the one we've created is really out of the question. So that's really what we were looking for to create as a product for people. And here I just wanted to show a little bit of a comparison in terms of, let's say, resolution or sensitivity. As you can see, we're comparing the synchrotron, or what is commonly known as magnetic force microscopy, or MOC, or SQUID. You can see that with these nitrogen vacancy sensors in diamond, and our CiQ, which is the name for our microscope, you really do have much higher sensitivity and a resolution as compared to all of the others. And we do think that it's relatively simple to use and very cost effective. So we try to portray this microscope as the new standard for high precision and resolution in magnetic imaging. So here's just a little bit of what the company has done. We have sold already several of these microscopes to universities and research institutions. The product itself is called the Qnami CiQ, together with quantilevers, which are themselves the nitrogen vacancy centers in diamond, which are used for scanning in the microscope. This technology is patented. We have a global footprint, so we have actually a very tight collaboration with atomic force microscope producer, which is called Horiba, and they have really a global distribution where they really help us, let's say, go to everywhere in the world, not only focus here in Europe. We do have some sales targets of around 30 units per year from around 2024. And here I really focused on the metrology for the semiconductor industry, because that was one of the main problems we saw that people were facing, at least in terms of magnetic fields. But we not only focus on that, we also have research and development towards thermometry. So what we call this scanning nitrogen vacancy thermometry, and we already have a patent filed for that type of technology. So we're not only focusing on magnetic fields or magnetism with our nitrogen vacancy centers, but we also think that they could be applied in many other fields, as I showed at the beginning. So we're also working on that. And yeah, well, so that I hope that quick talk showed a little bit about what a quantum sensing company does. We really help people find their problems, to see what issues they have with their current metrology tools, and see what we can help them with in terms of solving these problems or solving these issues. And yeah, lastly, I just want to tell everyone to join the Quantum Wave. We already have some job listings in our website for 2021. They're actually very specific for one of our subsidiaries that we actually have in Germany. But we also are open for internship opportunities. We have several projects running right now, and we don't have them posted on our webpage, but we know that we have them going on, and we always look for people that are keen on joining a quantum sensing company, and just get in contact with us. You will find all the details in our company website, and just send an email and we will get back to you to see what we can offer you. And we also have LinkedIn and Twitter. You probably find us there. Thank you. I will be open for questions now.
Thanks for that. And can I just say, I love the pun. Quantum Wave and Qnami.
Yeah.
Sorry. Always a pun. So we'll move swiftly onto the questions, if that's all right.
Sure.
Couple. So one of them is just saying, like, this looks amazing. I know it's not a question, but it's always nice to hear. And so next up, do you use bulk diamonds, or have you explored other color centers?
Well, I would say we really focus on nitrogen vacancy centers. So we don't use any other color centers for sensing. We know that people use them for research, but we really focus on nitrogen vacancy centers. And then it really depends. So as I mentioned before, for us, at least for our microscope, for this scanning NV magnetometry, we just use, let's say, pillars, where you have one single NV center at the apex, which is the one that is used for scanning. But several people buy bulk diamonds from us for their sensing applications as well. They can still use nitrogen vacancy centers in bulk for sensing. Typically, that would be more for wide field, let's say, optical sensing, where you use the whole diamond itself, not going point by point as you go in an AFM, but really using the whole bulk diamond as a sensing unit. People do that, and we do have let's say, products that go into that, but that is more related to what we call our quantum foundry. Here I just focused on the microscope, but yes, we do. So we have, and if you have a question about looking for nitrogen vacancies in bulk diamond, you can also find a bunch of information about that on our website. That we do.
Oh, okay. Well, I'm sure if they're interested, they can follow up. And either are you about on the gather time? Maybe they can ask you.
Sorry. Yeah, or if they have a very specific, if they have a very specific question, they can either ask you or through Slack. I can answer them.
Cool. So we've got a few more questions. Next is, does your microscope work for conductive samples only?
For conductive samples, well, I don't think I get the question. So what we use the sensors for is really just for magnetic fields. But of course, if you have a magnetic field, you can also have a current sensing, right? Like magnetic field and current go together.
Yeah.
So you could use the microscope for, let's say, conductive samples. If you have current flowing through, let's say, a wire, or if you have current flowing through a certain structure, you could also use it for imaging that. It really depends on the end application, but again, magnetic fields and currents do go together, so you can also use it for that if the question was going in that direction.
Yeah, but I'm guessing it's not a necessary condition, right? It doesn't.
No, not at all. It could also be like very, very weak magnetic fields coming from, let's say, discrepancies in the magnetic order of your material. That could also be. It doesn't have to be a conductive sample for you to be able to image it.
Cool. Okay. Yeah, I think that probably answers the question something better.
All right.
Next up, currently, what resolving power are you targeting? Which size do you think you'll be able to reach in the following?
You mean in terms of resolution? So in terms of resolution, we typically go for magnetic resolution, and like for the magnetic field, and that would be typically lower than 50 nanometers. But again, this resolution is very different as for, let's say, atomic force microscopy resolution, because that is typically more based on the size, not on the actual magnetic field or magnetic, let's say, domain or magnetic structure type of resolution. So those two things are very different. But if you're asking for magnetic field resolution, it would be lower than 50 nanometers for sure.
Yeah, I think they may be saying like kind of what size can you resolve with that?
Okay, so yeah, it would be if you would have a, let's say, a point source of a magnetic field, and that would be in the range of 50 nanometers, we could for sure resolve that. In terms of magnetic field, then again, it really depends on what we're talking about. Because then if you have a much smaller, let's say, feature, and if this feature does not have a magnetic field, then maybe not, right? Yeah. So I hope that answers the question.
I'm going to assume it does. Okay, so next up, we've got, so the characterization of superconducting qubits. Are there issues with compatibility of applying the required bias fit to the NVs? Operating under applied off-axis CiQ.
That is actually a very interesting question. So typically for let's say, if you're using superconducting qubits, you're typically being cryogenic temperatures. So we know of people using our nitrogen vacancies in like cryogenic temperatures. Then again, it does depend on the orientation of the magnetic field, right? Because NV centers could be used in high magnetic fields. Though the only, let's say, caveat of this argument is that the magnetic field has to be oriented in the same axis as the nitrogen vacancy. Probably we could go more into detail about that. We have some information about that on our webpage. But typically on a 100 diamond oriented diamond, the MV axis would actually be on the 111 direction. So that probably wouldn't work for superconducting qubits, because it's really not like, let's say, out of plane. But if you ever have a 111 oriented diamond where the MV axis is actually out of plane, probably you could use very high magnetic fields. Like it doesn't really matter as long as it is oriented in the MV axis, and you would be able to image them. I think that goes towards the question.
I think so. They mentioned an off-axis beacon. So is there any way you can deal with that, or is that?
Well, so if the magnetic field is off-axis in the MV, probably not. You do have let's see, a limit in terms of probably like 10 millitesla range. If the magnetic field is off-axis, you would usually not be able to see anything else, just because this magnetic field mixes the states of the MV, and you wouldn't be able to have any signal anymore. Which is why you would then try and go for different orientations of diamond, where you could change the MV axis, and then you change the orientation probably to align it to the magnetic field you're using. But if it's out of plane, I mean, if it's off axis, then probably the range limit would be 10 millitesla around.
Okay, thanks for that. Final question.
All right.
How would you advise a person who has interest in sensing and communication with a background in physics and making it a living as a business developer in a startup incubator?
As
what advice could you give to someone like that?
Wow, that's a very nice question. I guess. Yeah. As a business, so if you would want to develop your own business, having these types of let's say ideas, you would go for trying to solve an issue, probably as the metrology issue I showed in this next generation of computing, trying to look at what are people struggling with. At least as a business developer, you would really have to look for that. Like, what is the issue that, like, what can't people resolve? What can't people do with what is currently going on in the technology, and how can I solve that? I would say that probably look for that type of problem.
I mean, it feels like this is a field where there's a lot of kind of fertile territory for that, right? But
yeah, exactly. So there's a lot of, I would say there's a lot of problems that people have where there's really no solution in terms of what is available right now. So you could really think about, okay, how can I solve this problem with what I know, at least with what experience I have in quantum sensing or quantum communication, or the type of defects I know people are researching on. How could I try to apply that into a problem that the industry is having, for example?
Yeah, and I suppose there's no issue in like kind of contacting people and saying, okay, so how can I help?
Yeah, and probably if you're already in this field, I mean, either quantum sensing or quantum computing, of course, depending on the quantum sensor, the fields are not so big, right? Like you would definitely know who to target or who to see what they're researching on. Right? Yeah. So I would go for that. Yes, I can answer more questions in the Slack. I think we're close to time.
Yeah, so I think we've slightly gone over time, but that's because it was interesting. So
sorry about that.
No, it's my fault because I kept asking questions. So thank you so much for your time. I'm sure you'll be in the Slack, so if there's any more questions, please pop them in there.